All right, let's go ahead and get started. So today we're going to continue our discussion of advanced topics in Hamiltonian mechanics. So at the end of last class, we proved a result called Liouville's theorem. And although the proof was a little bit detailed, the basic idea is very simple. So the idea is that if we have a mechanical system parameterized by some positions qi and conjugate momenta pi, then the area of a region in phase space stays constant in time. So the picture that one wants to keep in mind is that if you start out with some blob of given area in phase space, then as you evolve in time, the position of that blob may change, but its area will not. And so while the position and the shape of the blob may change, the area does not. So that is actually a rather remarkable result, given that we make almost no assumptions about the system, aside from the fact that it has a Hamiltonian formulation. So this is true for all dynamical systems with a Hamiltonian formulation. And indeed, it's true not just for two-dimensional systems, systems with one dynamical variable and conjugate momentum p, as I've drawn in this picture here, but it's also true for systems with n dynamical variables and n conjugate momenta. And in this case, the quantity which is unchanged in time is the area, is the n-dimensional volume, the 2n-dimensional volume of this region of phase space. So in a sense, that means that what we have discovered here is a constant of motion. But it's not a constant of motion associated with any particular trajectory, but rather with a collection of trajectories that describe some region in phase space. So the question now is, what other exact results, or what other results can we understand for generic dynamical systems? So as you know, for a generic system, the equations of motion might be very, very difficult to solve explicitly. And indeed, you're very lucky if there exists some analytic solution to the equations of motion that can be written in terms of nice, simple functions that you can understand intuitively. And so our goal over the next week or two will be to try and understand a variety of other ways of thinking about the evolution of dynamical systems that does not necessarily require us to come up with an exact analytic solution to the equations of motion. So one of these tools is Liouville's theorem, and the next tool that I would like to discuss is the Poincare Recurrence Theorem. Yes? Continuous evolution. For mechanical systems, we always describe things in terms of continuous evolution. Now, before I state the Poincare Recurrence Theorem, let me just start with a few preliminaries. So in Liouville's result, we saw that although the area of a blob in phase space remains constant, its shape does not. And so there are two different things that could happen to the shape of some blob in phase space as you evolve in time. If you start with some nice compact region in phase space, such as the one I've drawn here, then it could either evolve to some other nice compact region, or it could evolve to something more complicated. So one possibility is that if you start out with a very small region in phase space, then it could remain nice and compact, and I say compact heuristically and not in a formal mathematical sense, at some later time. But the other thing that could happen is that the shape of the system could change dramatically. So it could change in such a way, for example, that you could have a blob, for example, with lots of long, thin tendrils, in such a way that although the area of the blob remains constant, the shape of the blob has changed dramatically. So what does this mean physically? So physically, if we have a system which, under some time evolution, starts with a small blob and ends with a small blob at some later time t, that means that the system is relatively insensitive to changes in the initial variables. So you could imagine starting with some initial values of position and momenta, and then evolving sometime to get some other value of final value of position and momentum. And then you could imagine perturbing the initial values slightly, changing the initial position or momenta in some way, either by introducing some noise into the system or just changing them by hand a little bit. And then you would ask whether the final state depends sensitively on the initial conditions. And the statement that the blob remains compact is the statement that the final state is relatively insensitive to initial conditions. Whereas if the shape of the blob changes drastically, then that means that the final state is very sensitive to initial conditions. Now, let's try and be a little more precise here. So I haven't told you exactly what I mean by a very small blob, nor have I told you exactly what I mean by the shape of the blob as a function of time. Instead, I've just been rather imprecise about what I mean by the shape changes dramatically in time. And so later on in this course, what I've decided to do is give you a lecture on chaos, where we will precisely quantify what we mean by a state being sensitive or insensitive to initial conditions. There, however, are several things that we need to discuss first by way of introduction to the subject of chaos. So the first thing that I'll do is describe the Poincare Recurrence Theorem. Then we will proceed to discuss Hamilton-Jacobi theory, starting at the end of class and then into next class. And then we'll proceed to discuss integral systems, which are systems where the final state is insensitive to the initial conditions, before finally proceeding to study what happens for non-integrable systems and at what point the motion becomes highly sensitive on the initial conditions, in which case we would say that the system is chaotic. So our goal over the next week or two is to work up to a precise notion of what it means for a system to be chaotic. Now, the Poincare Recurrence Theorem, I think, is really the starting point for this study. And it's a rather remarkable fact, and one that's not at all intuitively obvious. So, before stating this theorem, let me just start by considering carefully the case where I have a system with 1 degree of freedom. So let's consider carefully a system with 1 degree of freedom. So we just have a position and conjugate momentum p. Now, let's also consider the special case where the Hamiltonian has no explicit time dependence. So that means that if we were to draw a picture of phase space, then a simple way of analyzing the motion would be to draw the surface, the lines of constant energy, the lines of constant Hamiltonian on this phase space. So, for example, for the harmonic oscillator, these would be just circles or ellipses. But for more general systems, there could be some random looking contours of constant energy, say. Now, the statement, which you already know, is that if you start with some initial values of the position and conjugate momentum, provided that the area inside the curve of constant Hamiltonian is finite, then you are guaranteed to return to your starting point. So, for example, let's say we started with the momentum equal to 0 and the position equal to some value q naught. Then energy is conserved, which means that as you evolve in time, you would evolve along this line of constant Hamiltonian. And after some finite amount of time, you would end up traversing this curve of constant h before returning to your starting point. Now, I put in this proviso that the initial position had to be such that the curve of constant energy had finite area. That's just a fancy way of saying that I want to exclude the case where I have some unbounded motion, which would correspond to the case where the area inside that curve was infinite. So, for example, for the pendulum, we had two different types of trajectories, depending on whether or not the initial momentum and position were such that the motion was bounded or unbounded. So, for example, on one of these trajectories, the motion would be bounded, whereas on one of these trajectories, the motion was unbounded. So, for the time being, we will just restrict ourselves to the case where the area inside this curve is finite, and so you return to your starting point after some time t. It will be. It'll be periodic in the sense that you return to your starting point, but the period will be some complicated function of the Hamiltonian of the system. And indeed, if you remember our study of generic one-dimensional systems, we wrote down an integral formula to compute the period of an arbitrary one-dimensional system. For example, you did this on your exam for a system whose kinetic term was rather complicated looking. Okay, so that's all well and good. But let's now ask what happens for systems with more than one degree of freedom. Now, for systems with more than one degree of freedom, conservation of energy implies that if we start with positions q naught I and momenta p naught I, then at any later time, the Hamiltonian, or the energy of the system, will be equal to its initial value. So the motion of the system just because of conservation of energy lies on the surface of constant Hamiltonian, of constant energy. Now, of course, it's a little harder to draw a phase space in 2n dimensions unless n is equal to 1. But the way that you should imagine it is that you have schematically some phase space, which is some 2n dimensional space, and then you start with some initial position and momenta. And conservation of energy means that as you evolve the system in time, you're restricted to lie on some surface in phase space with constant energy. But so let's now think about that surface a little bit. So the total phase space has dimension 2n. And the constraint that the Hamiltonian is a constant is one constraint. So that means that this surface has dimension 2n minus 1. For example, if you had a system with 1 degree of freedom, then the surface of constant energy is just a line with dimension 2 minus 1, which is equal to 1. So the difference, however, between the n equals 1 and n bigger than 1 case is that when n is equal to 1, the surface is just a line, so your motion has to travel exactly along this line. But when your motion is a surface, the evolution of the system will take you along some one-dimensional trajectory on this surface. But because the surface is not a line, you don't know exactly where that trajectory is. That will depend on the details of the Hamiltonian and the details of your initial position and momenta. So the statement of conservation of energy with systems with more than 1 degree of freedom is not enough to completely classify the motion. So for a system with 1 degree of freedom, we could write down explicitly an integral formula, for example, for the period of an oscillation, for an arbitrary system. But we can no longer do that in higher dimensions. However, there's one remarkable result called the Poincare Recurrence Theorem, which says that if the 2n minus 1 dimensional volume of this surface is finite, then you will eventually return arbitrarily close to your starting point. I mean, let's just think about that for a minute. So, for systems with 1 degree of freedom, you know that you always return to your starting point, unless the motion is unbounded. Now, for a system with 2 or more degrees of freedom, there's no guarantee that you'll return to your starting point. But what this is saying to us is that even though we may never return to our starting point, and typically we will never exactly return to our starting point, we will always return arbitrarily close. So what does that mean precisely? That means that if I wait a sufficiently long amount of time, then the distance in phase space between the initial position and final position will be very, very small. So, yes, so there was a question?
Yeah, I was just wondering if you're on a separatrix, don't you take infinite?
Unless you're on a separatrix. So if you're on a separatrix, that's the sort of marginal case between bounded and unbounded motion. So the separatrix was a point where this surface of constant energy was not nice. It was not smooth. It sort of had a cusp. So I'm also, I'm making some implicit assumptions here. And one of those assumptions is that one of those assumptions is that this surface is sort of nice looking and doesn't have any cusps. So, there's some assumptions that go into this theorem, and namely the assumptions is that everything is nice and generic. And I won't try and quantify what generic means. Roughly speaking, it means that there's no cuspy behavior for this surface. Now, of course, this statement doesn't mean that at all late times, the motion is very close to your starting point. But it just means that there is some time in the future where your motion is very close to your starting point. So the picture that you want to keep in mind is that if here is your surface of constant energy, and you start at this point at time t equals 0, you'll wander around this surface for a while, and eventually you'll come back, say, within a foot of your initial starting point. And then you might wander around for a little while longer, and then you'll come back within 6 inches of your starting point. And then you'll wander around for a little while longer, and then you'll come back within an inch of your starting point. And the behavior of the system is always going to be such that no matter how close you demand that your final position is to your starting position, there's some time t such that you come within that distance. So I don't really want to go through the proof of this statement in too much detail, but I want to give you a little flavor for how this is proven. Are there any questions before I continue? Yes.
Classically, does this imply a recurring universe?
That's a good question. Our universe does not. So remember that in order for this to be true, the system needs to have a Hamiltonian formulation. Systems have Hamiltonian formulations when everything is conservative, and in particular, so energy is conserved. In our current universe, it does not appear that energy is conserved. For example, you've probably heard of redshift. Have you guys heard of redshift? Okay. That's the statement that roughly, because the universe is expanding, energy is constantly being dissipated. So in our current cosmology, it does not appear that there's no evidence which indicates that the dynamics of the universe as a whole is conservative. So no, there's not necessarily a good reason to think that we will undergo such a recurrence in our universe. However, there is also some theoretical evidence that such a thing, well, if you try and describe the universe as a system that can be governed by a Hamiltonian and has a unitary time evolution and has a compact phase space, then yes, that would happen. But it's an open question as to whether or not those assumptions are true for our universe. So that's a good question, and that is something we don't know the answer to. If you just plug in Einstein's equations for the evolution of our universe as it appears now, the answer would be no. But there are some theorists who try and come up with situations, who try and imagine situations where the answer is different. So it's an open question. Good question, though. Any other questions? Okay. Was there a question? No. Okay. So let me give you a little bit of a flavor for how this is proven. Now, there is a proof of this in your textbook. The proof is not terribly rigorous and is not really any more rigorous than the proof I'm going to give. The best place to look for a proof of this is either in the book by Goldstein or the book by Arnauld, which are somewhat more advanced. The Arnauld book is really the best place, but it's a bit more mathematical. But the basic idea of the proof is very simple. So the idea of the proof is that it is an easy consequence of Liouville's theorem. So let's imagine that we have some surface in phase space. And let's imagine that we want to say, show that at some time t, our final position will come within a foot of our starting position. So you draw a little blob whose size is a foot around our starting position. And then you imagine evolving for some time t. So then what will happen? Well, you'll have another blob. And because of Liouville's theorem, the size of that blob will remain constant. And then you evolve for some time, another time, and then you'll get another blob, and another blob, and another blob, and another blob. And you can see what's happening here. So because our surface has finite volume, and because the volume of the blob is unchanged as each step goes by, after I evolve for time t, which could be a minute or an hour or something like that, eventually what will happen is that I will fill up this entire surface. And eventually what has to happen is that two of these blobs intersect. And what happens when blobs intersect? That means that the motion has come very close to itself. And so, indeed, one could always evolve. Once you find two blobs that intersect, you could then evolve the system backwards in time to make one of those blobs our initial point, and then you'll find it, that'll give you another blob which overlaps with the initial point. And so what that means is that the initial point and the final point are then very close to each other. So the idea is to use Liouville's theorem so that phase space is covered by blobs. You know, I mean, if I were a mathematician, I wouldn't say blob, I would say ball of radius epsilon or something like that. But, you know, that's why it's good to be a physicist instead of a mathematician. And so because the volume of phase space is finite, whereas time is infinite, and so the volume covered by these blobs as I evolve in time is infinite, that means that these blobs eventually have to intersect. Are there any questions? Yes?
Why would the blob always cover different areas?
Well, they don't necessarily cover different areas. So you could try and come up with sort of pathological situations where all the blobs end up condensing at some point in phase space. You know, you could imagine that all the blobs end up all very near each other at some late time. That's one of these sort of special cases that you actually can rule out using the assumption that the system is generic. I won't try and do that. So, you know, I just want to give you a flavor of the idea rather than trying to prove it rigorously. Any other questions? So the Poincare Recurrence Theorem really tells us that, so the statement of the Poincare Recurrence Theorem says that one of two things happens. One possibility is that you actually come back to your initial starting point. So one possibility is that you return to your exact initial starting point. So in that case, the motion is genuinely periodic. So for example, in a lot of the systems with more than 1 degrees of freedom that we have studied in the class, the motion is genuinely periodic. You actually do return to your starting position after some time t. However, that is not the typical situation. And the typical situation is that you never return exactly to your starting point. And that what would happen is that if you started with your starting point and you just drew a line that described how the system evolved in time, then this line would trace all over this allowed surface in phase space, but it would never return to the starting point. And so in this case, there's a word that people use to describe that system. So the trajectory of the system would be, you would say that it is dense in phase space. Or at the very least, it's dense on the surface in phase space that is allowed by energy conservation. And so so if you think about it, I mean, it's a sort of funny situation where you have a 2n minus 1 dimensional surface that is completely colored by this one-dimensional line. So mathematicians love thinking about sort of pathological cases like this. But roughly speaking, what it means is that the motion is ergodic or dense in phase space. And so in our study of chaotic systems, we'll return to study systems where the motion is dense in phase space in some considerable more detail. Before doing so, however, what I wanted to do was spend a little bit more time discussing the formalism of Hamiltonian mechanics. And in particular, we'll discuss this first possibility, which is also known as integrability. In a bit more detail. And that's something that we might get to next class or the following class. I think it's sort of remarkable. I think the statement of the Poincare Recurrence Theorem is one of the most amazing statements in classical mechanics. And it's really true for any mechanical system. I mean, we really didn't need to assume anything about the details of the system, aside from the fact that it was suitably generic. So what it means, for example, is that I could study the classical system which describes the motion of all of the air molecules in this room. And I could imagine starting with an initial state where this room is vacuum, except that all of the air molecules are concentrated in one corner of the room over there. And as long as the dynamics of the air molecules in this room all tend to the 60, whatever I don't know how many air molecules are in this room, probably not 10 to the 60. That's about the number of atoms in the galaxy. But something like, 10 to the 30 air molecules in this room would eventually, after some very, very long but finite amount of time, all return to be very close to their initial starting point, where they're all sitting over there in the corner of the room. Of course, the point here is that the volume of phase space that one needs to cover is absolutely gigantic, because it's a 10 to the 30, it's a 2 times 10 to the 30 dimensional space. And so it is an absolutely huge amount of volume. And the initial volume that we're covering it with is very, very tiny. And so even though eventually it'll happen, the amount of time it would take is absolutely phenomenally long. And indeed, you could even estimate schematically the amount of time it would take by comparing the volume of phase space that is occupied by all of the air molecules in this room sitting in one corner to the size of the phase space of air molecules moving in some arbitrary configuration. So that's a fun exercise to do. And maybe, I encourage you to do it on your own just to have a good time. So this is what I wanted to say about the Poincare Recurrence Theorem. So a lot, I apologize that, because this is not a mathematics class, I'm not attempting to prove things to you rigorously, and so I've left out some details. But we're now going to proceed to study, a little more of the formal structure of Hamiltonian mechanics. But before I move on to do that, are there any questions about Poincare recurrence? No questions? Yes?
So it should be work like a definition of entropy?
Well, entropy is an interesting thing. Entropy in classical mechanics is not something that we typically talk about. Because in this class so far, we have been discussing the motion of a system where the number of degrees of freedom does not change in time. So we're imagining that we have an exact microscopic, so to speak, description of all of the air molecules in this room. And we evolve forward using a Hamiltonian, and the number of degrees of freedom does not change in time. In order to talk about entropy, there are two different notions of entropy. You can either talk about entropy in a statistical sense, which means that you coarse grain in some way and use some set of macroscopic variables like the pressure and the temperature of the air in this room, which are things that can, in principle, be computed out of the microscopic variables, like the positions and the velocities of all the air molecules in this room. But in practice, it's something that these are some coarse-grained variables. And then the other notion of entropy is a thermodynamic entropy, which is something similar, but not precisely the same thing as the statistical entropy. The statement that all of the air molecules in this room might eventually end up sitting in that corner over there sounds like it's something that violates the second law of thermodynamics. And indeed, in a statistical sense, the Poincare Recurrence Theorem is what is responsible for the second law of thermodynamics, because it says that if you start with a configuration of air molecules all in one corner of the room, eventually they'll spread out and cover the entire space in this room in some sort of uniform manner. And that's something that you would say thermodynamically is due to the second law of thermodynamics, because they would want to increase their entropy by doing so. Now, they might also decrease their energy, depending on the setup. So, but in classical mechanics, where you just track individual degrees of freedom and watch them evolve for all time, entropy is not really a concept that enters. So, the Poincare Recurrence Theorem is something. Essentially, what it says is that there are very, very rare fluctuations of a system that make it look like the entropy is decreasing. But that generally only happens because we're actually working in a framework where we have we're studying all of the microscopic degrees of freedom, and entropy is not really an appropriate notion to use in this case. But that's a good question. I mean, it does seem to fly in the face of what we think of as entropy. And the reason is that entropy involves some sort of coarse-grained description where we don't keep track of all of the individual motions of air molecules. Yeah, it's a very subtle issue. Any other questions? That's a good question. Yeah. Okay. So far in this class, you have learned three completely equivalent formulations of the laws of mechanics. So you have learned Newtonian mechanics. You've learned the Lagrangian formulation of mechanics. And you have learned the Hamiltonian formulation of mechanics. So these are three different, completely equivalent ways of understanding the mechanical behavior of the system. Today, I would like to teach you a fourth formulation of the laws of mechanics, which go under the name of the Hamilton-Jacobi formulation of mechanics. And much like the Hamiltonian formulation of mechanics, Hamilton-Jacobi theory is rarely useful for writing down equations of motion or solving the dynamics of a system from a practical point of view. But instead, it is useful from a conceptual point of view. And so, in particular, to my mind, the real import of Hamilton-Jacobi theory is that it makes the relationship between classical mechanics and quantum mechanics even more explicit than it was in the Hamiltonian formulation of mechanics. So Hamilton-Jacobi theory is another formulation of classical mechanics which makes the relationship to quantum mechanics even clearer than it was in the Hamiltonian formulation of mechanics. So let me just dive right in and start by presenting the basic formulation of Hamilton-Jacobi theory. So let's start by remembering something that we learned in the very beginning of this course. So in the beginning of this course, we defined the action of a system to be a functional over paths in configuration space, which is given by the integral of the Lagrangian. And the way that one thinks about this is you think about this as a functional, meaning a function of a function, which depends on a path qi of t through configuration space. And this definition of the Lagrangian is a definition that applies for any path in configuration space, not just the physical path that is taken by a system as it evolves classically. And the classical solution to the equations of motion, let's call it qi classical of t, is the solution which minimizes this functional. Okay, so that's something that you all know very well. So what I would like to do now is I would like to look at this action, and I would like to think of this action in a slightly different way. So rather than regarding this action as a functional, which depends on an arbitrary path through configuration space, what I would like you to do is I would like you to consider the action only evaluated on a classical solution to the equations of motion. And I would like you to think of that action as a function of three quantities. So what does it take to specify a solution to the equations of motion? Well, you need to specify the initial value of the positions, the final values of the positions, and if you wish to calculate the action of the system as it evolves from the initial to the final positions, then you have to think of it as a function of the time t that you are integrating the Lagrangian over. So we could define some function w, which is a function of 2n plus 1 variables, some initial and final positions as well as time, which is the action of the classical path that connects these initial and final positions in time t. Yes?
Just a question. The time t, is it final, initial, or the difference?
It's the difference. So this is the integral from 0 to t of L evaluated on Q classical. And Q classical is chosen by finding whatever solution to the equations of motion it is that connects you from Q final to Q initial to Q final in time big T. Yes? Yes. I suppose I should assume that my Lagrangian does not depend on time in order for this to be only a function of big T and not depend explicitly on an initial and final time. So let's consider the case only where my Lagrangian depends on Q and Q dot. So why does this always exist? I mean, it always exists unless you choose some particularly nasty values for Q initial and Q final. For example, if you're studying a pendulum, you want, the x and y positions of the pendulum to be those that are allowed by the motion. But as long as they're in the configuration space, then you can always find such a trajectory. So why is that? I mean, usually when you've solved the set of n second-order differential equations, you're used to solving them by specifying an initial position and momentum, or an initial position velocity. But you could also specify an initial position and a final position. Now, from a practical point of view, that's a very difficult way of going about solving a differential equation. Usually, if you think about integrating a differential equation, you specify only initial data, and then you use that to compute final data. But in principle, at least, you could imagine specifying n pieces of initial data and n pieces of final data, rather than 2n pieces of initial data. So in practice, this is not a terribly useful thing to do, but in principle, it's something you can do. And it's something that we will do because it will give us a very nice way of understanding exactly what the action of a classical system is. So this function W, which is really just the action of the system, evaluated on a classical path, depends on two n plus 1 variables, the initial and the final variables, as well as the time t that it takes to go from the initial to the final variables. So what I would like you to do for the moment is I would like you to just imagine keeping the initial values fixed and thinking of W as a function of the final values and time. So W, if you fix the initial value of the position, is thought of as a function of the final value of the position and time. So W is a function of position and time. And let's now ask, how does W depend on position and time? Well, in order to study how W depends on the final position and time, we need to understand how the action depends on the final position and time. So how does W depend on Q final and time? Well, let's imagine varying Q final. So Q final goes to Q final plus delta Q final. Then how does the action change? Well, if we change Q final, then the classical path that connects Q final to Q initial will change. And how does the action change under that classical path? Well, you've done this calculation many times, so I don't even need to redo the derivation for you. It's the sum of two terms, one of which is the dependence of the Lagrangian on the path. So that's the equation of motion times delta Qi summed over I. So this describes how the action changes as I vary the classical path. And if you remember from the derivation, there was also a boundary term, which was dl by dqi dot times delta qi. And that is evaluated at t and 0. Do you guys remember this derivation? Okay. Now, in our derivation of the equations of motion, we imagined holding fixed the endpoints and varying only those paths with fixed endpoints, so that this boundary term vanished. Here now we're doing the exact opposite. We're changing the endpoint of the path so that this guy here no longer vanishes. But we're still looking at classical paths which solve the equations of motion. So this guy here always vanishes. So what does that tell us? That tells us that if we vary the final position and demand that we compute the action always on a solution to the equations of motion between the fixed initial point and the final position which is varying, then to first order, the variation of the action is the sum over I dl by dqi dot times the variation of the final endpoint. So what does that mean? That means that this function w, which is just the action thought of as a function of the final endpoint on a classical path, obeys the derivative of w with respect to q final is dl by dqi dot, evaluated at t is equal to t. Now, we had a name for dl by dq dot. That is what we called the momentum. So if you ask how the action depends on the final endpoint, then the derivative of the action with respect to the final endpoint is the momentum at that end. It's the final momentum. Is that clear? Any questions on that? Okay, so that's how W depends on QI final. But W also depends on T. So what's the derivative of W with respect to T? So to compute the derivative of W with respect to T, let's imagine taking a classical path that goes from QI initial to QI final in time t. And then let's imagine just continuing along that classical path for an additional amount of time delta t. So let's just let that path run a little longer. We let the evolution run a little longer so that t goes to t plus delta t. And, of course, when you do that, the position will change as well. So QI final goes to QI final plus delta QI final. And so how does the action change when we do that? So here we're computing the total dependence of the action on time, which is the sum of two things. There'll be some explicit dependence of the action on t, along with some dependence that arises because the action depends on q final, and q final itself depends on t. So that will be the dependence dw by dqi final times the change in qi final over dt, which is qi final dot. And we already computed dw by dqi final. So this can be written as the partial derivative of the action with respect to t plus the sum over I qi dot final times pi final. Okay, everyone with me so far? I mean, it's a little sneaky. I freely admit that I'm being awfully sneaky here. First, I calculated the partial derivative of the action with respect to Q final by holding T fixed and varying Q final. Then I imagined considering a classical path and evolving that for a little while longer and asking how it is that the action changes in time. And that will have two components, one which comes from an explicit dependence on T, and one which comes from the implicit dependence of the action on Q final, because Q final itself changes when I evolve the path a little longer. And now I would like to make one further observation. So how is the action defined? The action is defined as the T integral of the Lagrangian. So if you take the derivative of the action with respect to T, that will just, by the fundamental theorem of calculus, be the Lagrangian. So it'll, as a function of Q final dot and T. Right, because the action is the integral of the Lagrangian, and so you take the derivative, you just get the Lagrangian again. So we can reorganize that a little bit, and you see that the derivative of the action with respect to T is the Lagrangian, or let's write it as the following. It's minus the sum on I, Pi, Qi dot, minus the Lagrangian. And of course, I'm leaving off the final subscripts. So these are all evaluated at Q final and P final. Now, hopefully, if I have done my job this semester, you will recognize this particular combination of P's, Q's, and L. This is the Hamiltonian. So, what does that mean? Let's just summarize what we have seen so far. So, if we fixed the initial values of the system, if we fix the initial position of the system, and we think of W of Q int, which is the action for fixed Q initial, and so we think of this function W, which is a function of position and time, which is just the classical action starting at a fixed Q initial and at a Q final, which is equal to Qi, and time big T equal to little t. So all I'm doing is I'm stripping off the final from Q and calling big T the same as little t. I can call it whatever I like. It's a free world, right? Then what differential equation does W obey? So W is some function of position and time, which obeys the following differential equations. So dW by dQi is equal to Pi, and dW by dt is equal to minus the Hamiltonian, thought of as a function of Qi, Pi, and t. And Pi, of course, is the same as dW by dQi. Right? That's just the first equation. So this is known as the Hamilton-Jacobi formulation of mechanics. And this equation here is known as the Hamilton-Jacobi equation. And it tells us how the action of a system depends on time. I would like you to stare at that equation in the box for a few minutes. So let's think about what this equation is saying. This equation is saying that if you take the action of the system, evaluate it on a classical path, and you fix the initial conditions, then this is a function of two things. It's a function of position and time. And the time derivative is equal to the Hamiltonian. Now, hopefully this statement is somewhat familiar to you. So this is very reminiscent of Schrödinger's equation. So what is Schrödinger's equation? Schrödinger's equation says that you have a wave function, which is a function of position and time. And if you take the time derivative, then that is equal to the Hamiltonian acting on the wave function. And so you can see here that the classical action here is to be regarded as the classical analog of the wave function. W is regarded as the classical analog of the wave function. And the right-hand side of this equation should be regarded as the Hamiltonian acting on W. So W is like a classical wave function. Now, you don't want to take this analogy too far, because the wave function in quantum mechanics has a somewhat different interpretation as the wave function in classical mechanics. In classical mechanics, W is an action which is everything is completely deterministic. You know, there's no amplitudes or anything like that appears in classical mechanics. Only probability, only deterministic evolution. But nevertheless, formally, I hope you can at least see that this boxed equation here is very, very similar in structure to Schrödinger's equation. And in fact, one can go a little bit further and make this analogy completely explicit. And since I have enough time that I think I can do that. But before I do so, let me ask if there are any questions. So let's just try and make this analogy a bit more explicit. So in order to make this analogy a little clearer, let's just consider a one-dimensional system. So, and I'll just take some normal system with dynamical variable q and a Hamiltonian, which is 1 over 2m p squared plus v of q. So particle moving in one dimension in a potential. So then what's Schrödinger's equation? Schrödinger's equation says that I h bar d psi dt is equal to the Hamiltonian acting on the wave function, which is minus h bar squared over 2m d psi by dq squared plus v of q times psi. Right? There's an h bar every time there's a derivative, along with those factors of I. Everyone hopefully knows this form of Schrödinger's equation. Okay. So what is the wave function physically? Well, the norm of the wave function is something that's totally clear. The norm of the wave function is the probability for the wave function to be, the particle to be at a given point. So let's break up this wave function into a modulus r, which is the norm of the wave function, and a phase. And for perverse reasons of my own, let's call that phase e to the I w of q and t over h bar. I'll just put that factor of h bar in. That's just part of my definition of w. And at this point, w is some arbitrary function of q and t. So this norm is the probability of finding the particle at a given point. And we would like a physical interpretation for the phase of the wave function. So let's go ahead and just plug this into the Schrodinger equation. So plug that into there. Well, let's write out the left-hand side of that equation. So the left-hand side of that equation is I h bar, and then there's two terms. There's a term coming from the derivative of r, and a term coming from the derivative of w. And then there's an e to the I w over h bar, but let's just we'll factor that out of the left-hand and right-hand sides at the same time. And what is the right-hand side? Well, we have a minus h bar squared over 2m. Then we have to take a bunch of derivatives. So there's the derivative of r. So there's the second derivative of r. There's the terms that arise by taking the, well, let's work that out a little more explicitly. I mean, can we do it in our heads? Let's do it in our heads. So we have a second derivative of r. Then there's the term where you take the first derivative of r, and then you take a derivative of the phase term. So there'll be a 2I over h bar, r prime, w prime. And then there are the terms where you take the derivative of the w term and then take the second derivative. So that'll give you minus r over h bar squared, w double prime. And then there's the one where you take the derivative of the exponent twice. So that'll be plus I r over h bar, w double prime. And then plus the potential times r. Everyone with me on that? Was that too fast? Oh, I'm sorry. One of those is w prime squared. Right. In order to derive this, we use the fact that d psi by dq is equal to r dot plus I w dot over h bar r times e to the I w over h bar. And so the second derivative is a bunch of different terms. There's an r double dot, an I w double dot over h bar r, a I w dot r dot over h bar, plus terms where you take the derivative here. When it multiplies by this term, you get a factor of 2, and then when it multiplies by this term, you get that term. Okay. So this is the wave equation that is obeyed by, this is the Schrodinger equation, where we break up the wave function into the radial and the phase part. Okay. Now, one thing that I know about classical mechanics, I know a lot of things about classical mechanics. I only know one thing about quantum mechanics. The only thing I know about quantum mechanics is that it's supposed to reduce to classical mechanics in the limit where h bar goes to 0. So when h bar goes to 0, this should reduce to classical mechanics. So in the classical limit, what happens to this equation? Well, you can now see why I put that 1 over h bar in the exponent when I wrote out the phase of the wave function. Because in that limit, if you look at the left-hand side, what does that become? That just becomes minus... Did I really get a minus sign wrong? Okay, well, we'll see. Minus dw by dt. And what does the right-hand side look like? Well, the only term that survives are the ones with no powers of h bar. So we have r over 2m. So I'm factoring out an overall power of r. So I have 1 over 2m times dw by dq squared plus v of q, plus terms that are order h bar. Everyone with me on that? So let's take that equation and let's compare that to the Hamilton-Jacobi equation. So the Hamilton-Jacobi equation says that the action of a system, regarded as a function of the final position of the system and time, evaluated on a classical path, obeys minus dw by dt is equal to the Hamiltonian evaluated on w with the momentum set equal to dw by dq. And that is exactly what appeared here on the right-hand side of this equation. The Hamiltonian is 1 over 2m p squared plus v. Set p equals dv by dq, and you get Schrödinger's equation. So what have we seen? In the classical limit, Schrödinger's equation, when you divide the wave function into a modulus and a phase part, just reduces to the Hamilton-Jacobi equation. So in the classical limit, the phase of the wave function is the classical action of the system. In the classical limit, the phase of the wave function is the action. Now, when you were studying your quantum mechanics classes, you sort of had no idea what physically you should think of the wave function as. I mean, you still don't really have an idea of what physically you should think of the wave function as. But in the h bar going to 0 limit, you now know exactly what the wave function is. The wave function is the thing whose modulus is the probability of finding a particle somewhere, and whose phase is the classical action. This is why the action principle is important. And this is why there is such a deep connection between the action principle and not just classical mechanics, but quantum mechanics as well. The action of a system is precisely the phase of the quantum mechanical wave function. I guess I've said that 3 times now. Are there any questions? No questions? So, we saw that the action formulation of a classical system was very useful for describing the classical evolution of the system. And in fact, this result indicates that the action formulation of a classical system is also very useful in the quantum mechanical formulation of that system. And indeed, this observation motivates what's known as the path integral formulation of classical mechanics, of quantum mechanics. The path integral formulation of classical mechanics is kind of trivial. The path integral formulation of quantum mechanics, however, is the statement that to each path in phase space we associate in configuration space we associate a phase. So in the classical limit, we saw that there is a classical path that the system takes, which is the phase of the wave function. So what about the non-h bar going to 0 limit? Well, fortunately, we know what the action is, even if you're not computing a classical path. Indeed, when we studied Hamilton's principle, we thought of the action as a function of all possible paths through configuration space. And so the action gives us a number for every path through configuration space. And this observation that the action is associated with the phase of the wave function tells us that if you want to write down the wave function of a quantum mechanical system as a function of Q and T, then you need to add up all possible paths that the system can take through configuration space, associating with each path a phase which is the exponent of the action. And here, when I integrate, I'm integrating over all possible classical configurations that start at some initial value at, say, time t equals 0, and end at some final value, let's call it Q final, at time t equals capital T. And this gives us an alternate formulation of quantum mechanics. So there's the Hamiltonian formulation of quantum mechanics, where you think of the wave functions as living in some Hilbert space, and time evolution is determined by the action of the Hamiltonian. Or you can think of your wave functions, which calculate the amplitude for a particle to be present at a given point Q final, and those are computed by doing an integral over all paths through configuration space, starting with whatever the initial configuration of the system was, ending at this final point at a given time, and you integrate over all paths weighted by this factor, which is e to the I times the action over h bar. And indeed, you can show that this quantity is a solution of Schrödinger's equation. I'm not going to show that because this is not a class on quantum mechanics. Did you do it in your class on quantum mechanics? Did you see the path integral formulation of quantum mechanics? Not really? No?
We had one lecture at the end of last semester.
I see. Yeah. So I think the motivation for the path integral formulation of quantum mechanics is rather unclear until you see the Hamilton-Jacobi equation. Because the Hamilton-Jacobi equation is the thing that really allows you to identify the classical action as the phase of the wave function in the classical limit. And then the path integral formulation is just a generalization of that when h bar is not equal to 0. And it also makes it clear to you what h bar is. H bar is the quantum of action. Action is a dimensionful quantity. It has units of energy times time. So you can't exponentiate it, because you can't exponentiate a dimensionful quantity. So you need something with dimensions of action that you can divide it by in order to exponentiate it. And the name that we give that quantity is h bar. So h bar, if you really want to think of the correct way of thinking of what h bar is physically, h bar is the quantum of action. Now, in fact, it's possible to show quite explicitly that this path integral formulation reduces down to the standard Euler-Lagrange equations in the semi-classical limit. Now, in order to do so, we need to understand how to take the classical limit of this formula. Is that something you did last semester in your quantum mechanics class? Okay. So how do we take the classical limit of this equation? Well, do you guys know, what's that?
Do we expand and then take?
Well, so what you need to do is you need to use what's known as the saddle point approximation, or the stationary phase approximation. Have you guys seen this? I think it's a real crime against humanity that you guys are not taught the saddle point approximation. I think that's a real shame. Because, like, there's so much physics. All of classical mechanics is the saddle point approximation. I mean, I think that's a fair statement.
Is it as saddle point in multivariable calculus?
It's the same as the saddle point approximation in multivariable calculus. Did you see this for doing multivariate integrals? So let me tell you what the saddle point approximation is. It says that if you're doing an integral dx of some function, let's call it s of x, then this is equal to the value, if this function has an extremum, then this integral is equal to the value of the function at the extremum plus subleading corrections. So if ds by dx evaluated at x naught is equal to 0. So what you should imagine is that s as a function of x looks like that, or I guess because of the minus sign that I put in, you should think of s as a function of x is looking like that, and then the value of this integral is very close to the value at the critical point of s. Okay, that's the saddle point approximation. That wasn't so hard. So let's apply that to this expression. And now everywhere we have a d, we just replace it by a script d, or by a Greek d, because we're dealing with functions instead of numbers. And so that says that the integral over all paths of e to the I action over h bar is dominated by the path where the derivative of the action with respect to that path is equal to 0. That's the saddle point approximation. And what is the statement that the derivative of the action with respect to a path is equal to 0? That's the Euler-Lagrange equation. Those are the equations of motion of a classical system. And indeed, you can actually prove the saddle point approximation is something rigorous in the h bar going to 0 limit. So for finite values of h bar, these correction terms that I've just written with a dot, dot, dot will not be negligible. But as h bar goes to 0, those correction terms vanish. So what does that mean? That is just the statement that in the h bar going to 0 limit, the phase of the wave function is dominated by the path such that ds by dq is equal to 0. What is ds by dq? That's the Euler-Lagrange equation. That's the classical equation of motion. Question?
Yeah, prove the ensuing principle from that
I'll leave that as an exercise. Now, much like the Hamilton-Jacobi formulation, the path integral formulation is not something that is practically terribly useful. Indeed, the path integral formulation was really only developed in the 1940s. And it was really, essentially the only problem that can be treated rigorously using the path integral formulation is the harmonic oscillator. It was really only in the 70s that people began to take the path integral formulation of quantum mechanics seriously. And that's because there were a variety of technical problems that arose in quantum field theories that can only be solved using path integral techniques. But I think it's always been clear that it's a very useful way of thinking about quantum mechanics and for understanding quantum mechanics. The problem, of course, being that we don't know how to define an integral over a space of functions. If you thought that defining a derivative with respect to a function was hard, you ain't seen nothing, because defining the integral over a space of functions is something that does not exist except in very, very carefully prescribed circumstances. So, for example, it's something that exists, there's a sense in which it only exists in as much as one can study the saddle point approximation and corrections thereof. So defining the precise definition of a path integral is a notoriously tricky question in mathematics, and not one that I'd like to discuss at all or think about at all. Any other questions? So I've gone on a little long. I can't help myself. Let's just pause and see if there are any other questions. Maybe I'll give you guys an extra 10 minutes next class. I mean, it's pretty cool stuff. Okay, see you on Thursday.